Today, let's talk about root mean square (RMS) value. RMS is very important concept for electronics for the AC signal. So, in general, if we have a AC signal like this, let's assume it's a periodical signal have a period of t, because it's AC signal, so we have the signal go both and go to the top side, also go to the bottom side, so the current basically go back and forth. Okay, so how do you define this AC signal, RMS value of these AC signals? Actually, you can base all the name here. Uh, let's assume it's a discrete format first. So we have a lot of sampling points along these signals, and with a signal with the name V, let's see VI. Okay, so then what is the RMS of these values in the discrete format? So we have go square first. So we take the VI squared, and then the mean values. Let's assume in one period we have n samples. So let's we take the sum from 1 I equal to 1 to n, then 1 over n. So that's the sum. That's the mean part. Okay, then we take the square root of this whole equation here. So that's basically the definition of RMS value in the discrete domain. If we look at this in a continuous domain like that, right? In a continuous domain, we can generalize this formula like RMS equals. So the summation basically turn into a integral. The integral that's integrate from one period from 0 to t, and the signals v t, which is a signal here v t. It's the signal is changing with the t, the time is the time axis, and we integrate over dt. So that's so we square here. So that's the square part, and the mean is 1 over t. So that's the mean over the one period, and we take the square root of that. So that's the definition of RMS value in the in a continuous domain. Okay, that's why this RMS value is important. What the physical meanings actually is. Okay, let's have this basic circuitry here. We have a resistor and a power source, and let's say we have a power source here, a resistor R. If the power source is a DC source, let's say it's a DC, in the case of one DC source, what's the power of this circuitry? Let's say it's V0. So that's very easy. It's V0 squared divided by R. So that's the DC case. How about what's the power of this circuit if the input signal is something like that? It's AC signals. It's a periodical irregular shape AC signals. And it's now they have two powers now, and a certain moment, for example, at this time here, we have a certain V, the voltage numbers, and the instant power at this point will be squared over R at this, and and when you go to the peak here, we get another value, instant power, and the V peak squared over R. So the instant power is constantly changing along the line, so it's hard to define. What we can define, a average power. What's the average power? So the average power is basically the integration of the instant power, V times t squared over R, over a certain time, integrate over 0 to t, the capital T, the period with the one cycle, and that's the power integrate over time. What you get is energy, basically the energy. The area under this curve is the energy. So the energy, if we know the energy, what's the average power, we just divide this by 1 over t, because energy divided by t, that give you average power. Okay, so now we know the average power for this irregular AC signal is like that. Let's do a little bit transformation here. If we move, if we remove R, because R is resistance, the constant. If we move R outside, it's integral. So we'll have 1 over R and 1 over T, 0 to T v squared T over dt. Okay, now then you can tell this part looks very familiar. It's exactly like that. This part basically is 1 over R and V RMS squared. Okay. Now, in the AC format, we just summarize here. In the AC format, for an AC signal input, the average power equals V RMS squared over R. Okay, so now this the physical meaning of this formula is very clear now. The RMS value for AC wave, basically that means it will produce same kind of power as the same value of DC voltage. Okay, so that's basically, you can look at the formula, it's very same. That means even the voltage signal looks very complicated and irregulars. As long as we know the AC, we know the RMS value of these AC signals, we can just use our familiar, we can just use all the formulas we know for DC signal processing, so like power and all the other stuff. So that's why RMS is so critical here. Okay, now let's have some fun. Just try to calculate the RMS value for a sinusoid, a sine wave, okay? Because that's just very easy, relatively easy to do. So if we have a sine wave, it will be something like this. And we have a, let's see, we have a peak value, V peak here, Vp, and the period is t. So the formula for the sine wave is Vt is equal to Vp times sine omega t. Okay, so omega is the angular frequency. So omega to the 1 period, the t should be equal to 2 pi phase. Okay. And to get the RMS value, VRMS in this case, we use the integration format, which is right here, and that will be, so we have Vp squared sine omega t squared first. Okay, then we integrate over from 0 to t and over dt. So that's squared and the summation, and over t, that's the mean part, and take the square root of that. Okay, and we can move the Vp squared outside, so that will give you Vp squared over t, 0 to t sine omega t squared dt. Now we can use identity for the sine wave, and the sine x equals 1 over cosine 2x over 2. Okay, now we can put this into here, and we can do square root Vp over t, 0 t, then 1 cosine 2 omega t divided by 2 and dt. Okay, and the 2 is a constant, so 2 can be moved out, so we move the 2 here, so we can get rid of the 2, makes it a bit similar. So it's like that. Okay, then what we have is here's Vp squared over 2t, and we first integrate the first part from 0 to t dt, because there's a 1 here, and integrate the second part 0 to t cosine 2 omega t and dt. Okay, and this looks like a lot of terms, but actually very simple, because cosine 2 omega t, the 0 t, we know if you integrate a cosine wave in a full cycle, the average will be 0, so this whole term will be 0. And so what this give you is basically just capital T, right? So what we get is, so we got Vp squared over 2t, and what we get from here is just t. So the t and t cancel, so what you left over here is Vp squared over 2. That means VRMS for a sine wave equals Vp squared, Vp can take it out, and Vp over square root 2. So that's basically the RMS value for a sine wave. That is Vp, the peak value, divided by square root of 2. Okay. Yeah, that's basically all for the RMS for now. Then next time we can talk about what happens if we have a DC offset. How do we calculate